Let's continue with the back page of the 5255 quiz review number 2. So number 5, if we look at this problem here, we know we have to deal with the definite integrals. We know we have to eventually evaluate the bounds. Again, just want you guys to be careful that we don't want to directly plug 1 and 3 into this problem here, because we haven't found the antiderivative yet. We have to evaluate the integral before we can plug in the upper and lower bounds. So we don't want to just go ahead and plug 3 and 1 into the expression before we take necessary actions. So if we look at we're going to try to evaluate the indefinite integral first. If we look at this problem here, looks like we don't have a single rule that will allow us to solve this complex problem. There's too many parts to this problem. So if that's the case, then we usually want to, the first thing we try to do is try to simplify this problem, and the way we do that is usually using U substitution. So we look at this problem and we think about what are some what's a candidate for the U value, right? Maybe the U value is the x squared. Maybe the U value is the entire numerator, e to the 3 over x, or maybe the U value is just the exponent, 3 over x. So if we think about what could potentially work, or maybe eliminate the possibilities that will not work. For instance, if we let the U value be x squared, the derivative will be 2x, and that 2x is not going to help us deal with that exponent at all. If we let the U value be e to the 3 over x, then the derivative is going to be e to the 3 over x times negative 3x to the negative 2, and that's too much to match with the denominator here. So I think that kind of takes us to, well, what if we let the U value be the 3 over x? So let's try that. So if we let the U value be 3 over x, we want to find the derivative, but let's go ahead and set this up so that we can prepare it for power rule. So to prepare for power rule, we'll bring the x up to the top, make it 3x to the negative 1. Now we can go through derivative power rule, which is bring down the negative 1, so negative 3x to the negative 2. And if we clean this up a bit, we get du over dx equals negative 3 over x squared. If we do cross product, remember the idea, once we find our U value and derivative, we're trying to replace all of these terms in terms of U. So we want to find a substitution for this dx, because we want to replace the dx in terms of U and du. All right, so cross product, so dx, negative 3 dx equals x squared du. If I want to solve for dx, I can divide by negative 3. If I divide by negative 3, now this is my expression that I'm going to plug into the dx. So dx gets replaced with negative x squared over 3 du, which is here. The 3 over x gets replaced with the u, and then the x squared, we're going to let it stay and see if that will cancel out. So the x squared, we do see that it does nicely match with the x squared from the substitution for the dx. However, there's a negative 1 that we don't want to forget, so we're going to pull that negative 1 in front along with the denominator, this coefficient 3, which can pull out as negative 1/3. So if we pull all this out, and if we cancel out the x squared, now if you look at the integrand, we have a nice expression that we have a rule for. The integral of e to the u is simply just e to the u. And we can replace the u value back in terms of x and then plug in the upper lower bounds. But what I did was I decided to keep the bounds, to convert the bounds, sorry, in terms of u, and then just use this and just evaluate the integrand in terms of u. So to do that, my initial lower bound in terms of x is 1. So if I plug 1 into the 3 over x, because that's this is the equation that relates to two variables, u equals 3 over x. If I plug 1 in for x, 3 over 1 is going to be 3. So that's my new lower bound. My new lower bound is 3. My initial upper bound is x equals 3. If I plug 3 in for the x, 3 over 3 is 1. So my new upper bound is 1. Now, it's sometimes, if we go through this conversion, we may end up with a lower bound that ends up being a higher value than upper bound, but we're not going to have to do any adjustments. We just have to if we want to go through conversion, whatever the upper bound turns into, it'll stay as the upper bound. Whatever the lower bound turns into, it'll stay as lower bound. We would have to go and adjust the smaller and the smaller and larger values. All right, so upper bound first. Upper bound gets plugged into the u value. So negative 1/3 e to the 1, okay, minus, then we plug in the lower bound. So negative 1/3 e to the 3. The two negatives cancel out. We're left with negative 1/3 e plus 1/3 e cubed. Number 6, integral of 2x over 1 minus 3x. All right, looks like we don't have one rule that will handle this. We also can't split this up into individual terms because we have too many terms in the denominator. So maybe let's look at u substitution. So our first candidate's first try would look to see if the denominator will fit as the u value. So we'll let the u value be 1 minus 3x. Our derivative is going to be negative 3 because 1 goes to 0. Negative 3x goes to negative 3. Solve for dx. Cross product, dx equals du over negative 3. All right, let's make the substitution and see how that works out. 2x will stay initially. The 1 minus 3x gets replaced with u. The dx gets replaced with du over negative 3. All right, now notice that the negative 1/3 comes out in front. The 2 also comes out in front. The problem is that there is still this x. We can't continue with integral rule if we have a remaining x in the problem. We have to convert everything in terms of u. So looks like the x is not canceling out, but let's go back to our assignment that relates to two variables. What if we replace the x in terms of u through this equation? So if I can solve for x, then I can replace my x in terms of u, right? So our u value is 1 minus 3x. If I try to solve for x, I can bring the 3x over, subtract u over, so 1 minus u. So x is equal to 1 minus u over 3. Now if I plug in 1 minus u over 3 in for this x, then my entire expression will be in terms of u, and that will bring me one step closer to be able to have a rule that we can apply. So that's our next step. Replace our x in terms of u, so 1 minus u over 3. I'm going to distribute the 2 through here, and we are dealing with some complex fractions, but we're going to try and keep these parts clear here. So distribute the 2 through. I get 2 times 1 is 2. 2 minus 2u over 3. And I'm going to pull the 2/3 out, and then just have the 1 over u over 1 minus u over u, and then du over negative 3, and I'll continue to combine the coefficients together. So negative 2 over 9, 1 minus u over u du. All right, now there's only one term in the denominator. Now I can split this up into individual fractions here. 1 over u minus u over u. U over u is just 1. So now we have to find the integral of these terms in terms of u here. So integral of 1 over u is natural log of u, right? Integral of 1 is just going to be power rule. This is in terms of u, so it's going to stay as u, and then plus c. Okay. All right, so now we can distribute the negative 2/9 through. So negative 2/9 natural log of u minus, there should be 2/9 there as well in front of this u. So I should just have a bracket here. Negative 2/9 bracket is going to affect every term in this expression, in this integrand. So negative 2/9 should be applied to both these terms, and then the u gets replaced in terms of x, and then we don't want to forget the plus c. All right, 7. Looks like we have a rule for secant of u, which is natural log of secant u plus tangent u. We should have to make some adjustment with this u value, because this u value will produce a coefficient that we don't want to lose track of. So we'll let the u value be 1/2 x, or x over 2. The derivative will just be 1/2. Solve for dx. Dx equals 2 du. We make our substitution in terms of u. X over 2 gets replaced with u. Dx gets replaced with 2 du. We can pull the 2 out in front. So now we have a nice clean rule that we can use. Integral of secant u is natural log secant u plus tangent u plus c. Sorry, the absolute value. Don't forget that. And then replace our u value back in terms of x, which is x over 2. Number 8. Integral of 4 to the 3x over 1 minus 4 to the 3x. All right, if we let Again, if we have to choose between numerator and denominator, choose the denominator first. Let that be your first option if you're having to choose between two options to decide what the u value could be. All right, we'll let the u value be 1 minus 4 to the 3x. The derivative of 1 is going to be 0. The derivative for 4 to the 3x, remember the rule for a to the u. Base a is going to be a to the u times u prime. So also the natural log of a. So this is similar to the rule for e to the u, except we have to adjust for the fact that this is not in terms, is not base e. This is base a. So we have to convert to base e to make that adjustment. So the integral of derivative for a to the u is natural log of a times a to the u times u prime. So natural log of a, the a value is 4. So natural log of 4 times a to the u, 4 to the 3x, times the derivative of u, this u prime. So the derivative of 3x is going to be 3. That's our derivative. If I do cross product here and solve for dx, I get du over negative 3 natural log of 4 times 4 to the 3x. Let's make our substitution here. Denominator gets replaced with u. 4 to the 3x stays initially. Dx gets replaced with du over negative 3 natural log of 4 times 4 to the 3x. Notice the 4 to the 3x cancels out. Negative 3 natural log of 4. All this is just one number that we can pull this out in front. And the integral of 1 over u. Now we have a nice rule for 1 over u. Integral of 1 over u, which is natural log of the absolute value of u plus c. And then now replace our u value back in terms of x. All right, number 9 here. Integral of cosine over 2 sine of x dx, 2 to the sine of x dx. This is too much for one rule to handle. So again, if we're having to choose between numerator or denominator being the u value, let's try the denominator first. We'll let the denominator be the u value. Well, actually, what happens is if we let the denominator be the u value, then our derivative will be 2 natural log of 2 times 2 to the sine of x times cosine of x. And if we think about that derivative, it's going to be too much for this cosine of x to match up. So so looking ahead, seems like that a to the u, this 2 to the sine x, will be too big of a u value for the remaining expression to handle. So why don't we let the u value be the sine of x, just that sine of x, be that exponent. All right, so we'll let the u value be sine of x. Well, actually, I'm going to bring the 2 sine of x to the numerator here, because we want to do a rule for a to the u, and we can't do a rule for a to the u if that a to the u is in the denominator. So first step is going to bring this up to the top to make things easier for us later on in the problem. Okay, so now the exponent is negative sine x, so let's let that be the u value. Derivative is going to be negative cosine of x, right? Sine becomes cosine, but then the negative will just continue through here. Will also be affecting the cosine x. Solve for dx, which is du over negative cosine x. Replace dx with du over negative cosine x. Cosine x stays. The negative sine x gets replaced with u. And now notice that the cosines cancel out. We have a -1 coefficient that we have to make sure we don't that we have to include. And then the integral for a to the u is just going to be 1 over ln of a times a to the u plus c. So 1 over ln of 2 times 2 to the u plus c. And then replace our u value back in terms of the original variable, which is negative sine of x.